Professor Israel Wachs of Lehigh University. He's a recognized leader in combined spectroscopic and operando spectroscopic techniques. He's received a number of important awards, among them Germany's Humboldt Research Award, the Hermann Pines Award, and the Langmuir Lecture Award. He's also the editor of the book Characterization of Catalytic Materials. And today he will share some of his new findings regarding water-gas shift reaction over bulk chromium iron oxide mixed oxide catalyst. This is a combined operando Raman IR SAS and XPS investigation, and his co-authors are Cr2O3, Emma Gibson, Rilya Vasic, Franklin Tao, Anatoly Frankel, and
Thank you for the introduction. Great pleasure to be here, to be invited to the Burke's Symposium. Congratulations, Burke, well deserved. I know that Burke spent, well, I should make a comment. I've interacted with Burke a little bit on Fischer-Tropsch, although I've not done this maybe almost 30 years, so I don't have much new to say about that. Through the Catalyst Society and on the executive committee, I've interacted with Burke, and he's probably one of the nicest people in the catalysis community, in addition to being a researcher. So even though I don't have anything to say about Fischer-Tropsch today, Burke's also interested in water-gas shift. And I've been doing some work in the recent years on water-gas shift reaction, which also, of course, especially occurs during Fischer-Tropsch reaction. And so the commercial catalysts for water-gas shift, the high temperature and medium temperature water-gas shift catalysts are chromium oxide, iron oxide, mixed oxide catalysts. And looking at the literature, as I'll review in a minute, there really has been very little direct observation of the catalyst during the reaction. Mostly people have looked at the catalyst before or after pulling it out of a reactor. And we wanted to combine the latest cutting-edge techniques that we have available to us. And I pulled together some people who have some of the best laboratories, like to do really so-called operando spectroscopies, combining the various techniques with the online mass spectrometer for simultaneous analysis, so we could get conversion selectivity results as well as seeing what's happening on the catalyst, in the catalyst bulk and surface phases. So to do the Raman, this part was done at Lehigh University. The infrared we did in collaboration with Mark Ledatouri and Emma Gibson at Caen in France. And to do the X-ray absorption spectroscopy, we did it at Brookhaven National Lab with Anatoly Frankel and his postdoc, Rilya Vasic. And this group is from Yeshiva University. And also Franklin Tao, we did some in situ, which is actually not listed in the title, in situ XPS measurements with this new instrument that Franklin has at Notre Dame. And so collected 4 groups here to do this work. So let's look at the literature and the history of the water-gas shift. It's a well-known technology. Originally it's chromium iron. More recently, copper's been added, and as time permits, I'll also talk about a little bit about what copper is doing here. So this is the water shift reaction that occurs at these temperatures. It's the high temperature reaction conditions. If you look at the literature, what the literature does agree is that the iron in the catalyst is magnetite, Fe2O3, and then this is referred to as the active phase during water-gas shift. However, people have, well, there's been some old in situ Mossbauer studies, but most of all the other studies was one. All the other studies have been by pulling the catalyst out from the reactor. This material is pyrophoric. It oxidizes when you pull it out, and so it is changing, and you really should characterize it during the reaction conditions. And the conclusion from this early work is that the active site is a iron 3, iron 2 redox couple. what is the role of chromium? Well, the literature claims that the role of chromium oxide is a stabilizer to reduce sintering of iron oxide. The iron oxide will sinter. XPS studies and high resolution scanning transmission electron microscopy studies have indicated that there appears to be excess chromium in the outer surface of the catalyst. But beyond that, and these were catalysts pulled out of the reactor. They're not looking at it during the reaction. Actually, this work done by Topso a couple of years ago was really the first in situ kind of experiment that did X-ray absorption spectroscopy. They didn't look at iron chromium, but they looked at iron copper chromium, and their focus was really on copper. But they did indicate that the chromium was present as +3 during the reaction. And again, the paper did not really focus on the chromium. And if you look at all of this, there's really no fundamental catalyst molecular structure information during water gas shift reaction conditions present in the catalysis literature, with the exception of this last recent publication. So we wanted to go in and look at this old problem and look at it from a modern perspective. I also want to point out that there are two mechanisms floating around in the literature for water gas shift. And one is referred to as the associative mechanism, that CO and water react to form some intermediate complex on the surface. Most common intermediate people invoke is a formate intermediate. But there's no evidence supporting this. There's no direct evidence to show that this is the case. In fact, there are no IR studies been reported in the literature to show this for these catalysts. The second mechanism is one of a redox, where the water reacts with a vacant site in the catalyst, giving up the oxygen and generating hydrogen. And in the second step, the CO picks up the oxygen and makes CO2, regenerating the empty site. So I want to first look at what does the catalyst look like during the reaction, and what can we say from the information we have about this mechanism. So this is the strategy that we took to learn about the catalytic active structures during the water gas shift. We performed so-called operando-Raman spectroscopy, hooking the Raman spectrometer in the reactor to a mass spec online. We performed also operando X-ray absorption spectroscopy with a mass spec online at the same time, to get information about the iron and chromium and structures and oxidation states, to get at the surface information, the oxidation states of the chromium and iron. Particularly chromium, we turn to in situ atmospheric pressure XPS. This is Franklin Tau laboratory. Yes, the only, to my knowledge, lab scale instrument that's able to do this in the USA, and to get information about surface reaction intermediates during the water gas shift, we turned to operando spectroscopy to be able to see what's on the surface. And basically this shows you how we treated the catalyst. We first heated them up in air and oxygen to 350 C, and then we exposed it to the different conditions. We did both reverse water gas shift and water gas shift. The reactions are in equilibrium, so at the end of the day, you get the same steady state results. And then we also cooled it back down slightly and oxidized it to see how, you'll see some things are reducing. We wanted to see what is reoxidizing, and we found it to be very informative when that happens. So the way the catalysts were prepared was by incipient wetness impregnation of chromium nitrate aqueous solution into iron oxide powder, and we varied, as you'll see, the H2CO ratios or the H2O ratios to match the initial catalyst reduction that you find also in the forward water gas shift experiments. And so we looked at various compositions. So the first question is bulk structure. What is the bulk structure of these iron oxide-based catalysts? And this is here done with Raman spectroscopy. And so this is the intensity, and here you have the various vibrations. And this is pure iron oxide. We examined this for many, many different H to CO2 ratios at this temperature, and actually also looked at some different temperatures as well. Basically, the results were the same. So you see these peaks here, and it turns out that the original iron oxide under these conditions is both the alpha Fe2O3 and the gamma Fe2O3. They have very distinct signature vibrations. As we start running the water gas shift, note that after about 10 minutes the bands are gone. So either the material totally reduced or it's transforming. And it transformed because after the loss of the Fe2O3 bands, what appears now is the Fe3O4. And all these new bands that we see are due to magnetite. So indeed, the iron oxide becomes magnetite under the water gas shift reaction condition. This is the mass spec signal just showing that we're doing water gas shift during this time. What about the surface? So again here we're looking at Raman spectroscopy. Now this time we've added the chromium to the catalyst, and again this is the Raman intensity, and here's the vibrations. And at the beginning of the reaction, you have this band at 1,000 wave numbers. This band is this structure of dioxochromium 6. And there's a stronger band here at 835. It's the bridging chromium oxygen iron band. And these are the iron oxide Fe2O3 bands. Again, when you start the reaction, and after a while it becomes amorphous, it's transforming, and it comes back again as Fe3O4 magnetite. Notice also during this transformation, this time we don't come back with chromium 6. We lose the chromium 6 species on the surface, their signature. Again, the water gas shift reaction is occurring during this reaction. To learn more about what's going on to the chromium, we turn to in situ hexanes. So again, here is the hexanes information. Here's the mass spec confirming that we're doing water gas shift. So we start off, you get this nice pre-edge. This pre-edge here is chromium 6. Okay? And this is the cap oxidized at the reaction temperatures. The pre-edge is still there. From the water gas shift, and the pre-edge is almost gone. We see new features appearing. These new features are of chromium 3 oxide. So we've reduced chromium 6, we start seeing chromium 3. Now we reoxidize it at the end to see if this comes, the original chromium 6 comes back. As you can see, it is not coming back. So maybe just slightly coming back up here. This is the water gas shift, and this is the reoxidized catalysts. Okay? A slight increase in this feature. So most of the chromium here apparently is lost and stays, as you can see here, as chromium 3. And so we know we start off with the chromium on the surface. The chromium goes in. A lot of it is stabilized during the transformation of Fe2O3 to magnetite. But the question is there any chromium on the surface, and what is its oxidation state? And this is where we turn to Franklin Tau with his unique in situ atmospheric pressure XPS system that allows you to monitor the oxidation states of, in this case, chromium. Also looking at iron, but it's not necessary to show that. And here is the starting point at room temperature, and you have here the peak for chromium 6 and chromium 3, because now we're trying to see what's on the surface. So we know we start off with this, and during the reaction, the question was, is there any chromium 6 left on the surface? And you can see that there's still a small amount of chromium 6 left, even though we're creating a lot of chromium 3, which is subsurface chromium. You can see here about 15% still retained as chromium-6. And so this raises a question: if chromium-6 is on the surface, is it the catalytic active site, or is it the iron oxide? We know iron oxide can do water gas shift, but is chromium acting, if you put the chromium on the surface, is it also acting as an active site? I should point out that we measured the ET surface areas, and indeed, the chromium is a stabilizer, and it increases the surface area of the iron oxide. But the question still remains, is this an active site? And this is another study, and again showing that the chromium-6 is still there under the water gas shift reaction. This is for 9% higher loading of chromium. The previous sample was for 3% chromium. Commercial loading is about 11% chromium oxide on an aluminum water gas shift catalyst. So with these characterizations of Vulcan surface, I've told you what's going on to the catalyst. Let's look at the reaction mechanisms. Remember, there were two reaction mechanisms. Can we get information about one versus the other? Since formate was the dominant species invoked for the associative mechanism, we absorbed formic acid on iron chromium. And here is the vibrations, and these vibrations, some physisorb here, residual amount of physisorb formic acid. But as you heat it up, all you're left with is this bridged, this bidentate formate species on the chromium iron catalyst. And the important point here is that this species is stable till about 300 C, okay, which is the lower temperature range of the water gas shift. Actually, you can still get water gas shift, as I'll show you in this temperature range. So now we know what the vibrations, there are different kinds of forming catalyst surfaces. There's monodentate, there's bridged, there's bidentate, and on chromium iron catalyst, we have the bidentate form. And now we know its vibrations, and we're going to see what happens during a reaction. So we start the reaction, and these steps as we're lowering the temperature. And we went all the way down from 400 degrees C, we started, and we lowered it down to 200 C while we're doing this. And while we're doing this, decreasing the temperature, here is the IR spectrum. And this is gas phase CO2. And the point to make here is that this has never been measured, even though formate has been invoked consistently for decades as the intermediate. It is just not present. We just do not see any formate during water gas shift reaction, even at temperatures. Remember that the formate was thermally stable till 300 C. So this was a region where we should have seen formate if it were a intermediate, and it was not there. So that is the mechanism. There's no evidence to support the so-called associative mechanism. So then we turn our attention to the other mechanism, which is the redox. And here, so we did the following experiment. It's a temperature program experiment. And first, we heated the catalyst in CO and argon, using CO as a reducing agent to make CO2. And this is the results in the mass spectrometer from this temperature program reaction study. And you can see that indeed, at very low temperatures, 205 degrees to 52, even 400, you're making CO2. In other words, CO is able to extract oxygen at very low temperatures. And remember, this is the region where formate would have been stable had it been being formed. Okay? Then, since the catalyst now has been reduced by CO, we hit it with water to reoxidize it and to make hydrogen. And here again, you can see hydrogen being produced at 140 degrees, starting at 140, and go up to 342. Again, the shaded area is where we would have seen formates that have been there. So the redox behavior is consistent with the mechanism being the redox mechanism, because you can do redox at a very mild temperature, much lower even than typical water gas shift reaction for this catalyst. The last part I want to talk about, this is more recent work, is copper promotion. So it's discovered a few decades back that the addition of copper further enhances the activity. And so we want to understand what happens. And so this is again an in situ ambient pressure XPS experiment. And this is the starting material, chromium-6 with a little chromium-3 on the surface. And during water gas shift, you see again this chromium-6 present and chromium-3 present. Okay. So again, showing that I forgot to mention that the chromium-6 being reduced to chromium-3 and on the surface it is responsible for the redox cycle in the chromium ion catalysts. This is the in situ XPS of copper, and initially started out with the copper oxide being present, but very quickly we reduced the copper metal. Not only that, you see that within minutes the copper signal, the metallic copper, is disappearing, and so the copper oxide is reducing very, very quickly. And the reason to metal, the reason we're losing the signal is that it's centered. And so the copper reduces and it centers, and it's present as large metallic particles in this gas shift catalyst. What does it do? Well, what are the consequences? So I'm showing you here the hydrogen temperature program reduction of the catalyst. The catalyst, this is iron. At the bottom, this is what happens when you add chromium because of the reduction properties. This is what happens when you have copper. And these catalysts are treated under water gas shift reaction conditions. So not fresh catalysts, they are in active. And you can see that tremendous ability of the copper to reduce, and the more you add, the more you have the reduction of catalyst. And so copper is associating hydrogen and enhancing the spillover of hydrogen to further activate and create the redox on the chromium catalyst for the water gas shift reaction. So to conclude, the characterization is that Fe2O3 magnetized is indeed as claimed in the literature, the bulk iron oxide phase. But again, most of this has been after the reaction. We do find literature has totally negated the possibility of being present, and we do find that these species are present, although the majority of them are reduced to 3, which Cr2O3 is isostructural with Fe2O3, and the chromium dissolves, but there's still maybe 15% residual chromium 6 that's redox, and a very important role as a catalytic site for the water gas. The oxide that's really there reduces to metallic copper and centers. Its role is to facilitate hydrogen reduction of the catalyst. As far as the reaction mechanisms, the associative mechanism, not only do we not see acid forming on the surface during the gas shift, we do not see any surface medium whatsoever. And so even the mechanism by many people, many decades, no one provided any evidence to support the presence of surgery. And so in terms of the redox mechanism, indeed the catalyst is able to give up oxygen and reoxidize, give up oxygen to CO2, oxidize water at temperatures that are both the reduction and oxidation temperature are lower than the water gas shift, indicating that this appears to be a feasible mechanism for this reaction. And we'd like to further propose that since there is some residual chromium-6, which is very easy to reduce, that this chromium-6-3 redox couple is responsible for this redox mechanism of these water gas catalysts. I'd like to acknowledge the various people here that participated. These are the people in grant that did IR work, a student uh, the international grant to go to work in France, and Franco is a postdoc relative with the Institute of Exchange Studies at Brookhaven, and these are the people that Brookhaven also assisted with these work. And finally, since we have more surface information and let all the information about from the exchange, we turn to Frank now. They was very gracious in providing complimentary information that allowed us to reach our users. So thank you very much for your attention. Answer any questions.
Any questions? Yes.
Evidence that the chromium itself is a good water gas shift count?
Good question. I don't know. It's a very low material. It's interesting.
Yeah, I mean, yeah, turnover.
It's worth you know, students may have looked at that. I just don't have in my head what the results were, but it's worth looking into. Because there are Cr2O3, you know, view it being chromium-3. If you do a surface analysis, and surface analysis, you'll find it's chromium-6. You see it like infrared. You can see the chromium oxide vibrations. So it has the structure that will allow it to do chromium-6.
Yeah, that's what I was thinking of.
Yeah. So my gut feeling is there's no reason why it can't.